product between some new point x and the support vectors xi, and then I multiply it by the alphas, sum them up, and build my classifier. That dot product element, or that dot product structure, is what makes what we're about to do work. Having done this, let's see, what have we done so far? Well, what we've done is we've figured out the best possible line in sort of 2 dimensions, okay? Well, great, except what if, suppose my features are not in 2 dimensions, okay? And also, I've been sort of assuming that I could actually draw a line. Well, what if my categories are not linearly separable, all right? And what if I have more than just 2 categories? Well, what we're going to do is we're going to knock down those questions one at a time going forward for SVMs. So we're going to start with, what if the features are not 2-dimensional? Okay? Well, actually, nothing about what I showed you in the math required that it be 2D, right? W dot x, I didn't tell you that x has to be 2-dimensional. No, it can be any dimensional, or d-dimensional, n-dimensional, whatever you want. It's just basically, you're now, instead of using a line, you're creating a hyperplane. The math is exactly the same, because remember, a plane is, remember how a line was defined, in fact, so in 2D, a line was defined by the normal. Well, in 3D, oh, this is going to be priceless, a plane is defined by the normal, right? So as long as I have this normal W, I'm getting a plane. In 3D, it's a real plane. In ND, it's an n-1 hyperplane. But other than that, all the math is the same. And in fact, using just that machinery, you can actually do some pretty cool stuff in computer vision. Probably the best known example, and this is one of the even though SVMs had started making their way into computer vision beforehand, I think the one that really sort of helped put it on the map was this work by Dalal and Triggs in CVPR 2005 for just doing person detection. And basically, they were taking upright person detection. The thing that you need to know is, basically, they cut, I'm not going to do any more than that, they cut their pictures up into cells, and they built little histograms of the oriented gradients in that cell, okay? So the features were called HOGs, histograms of oriented gradients. That's what this HOG stands for. And then you take one and here and here and here, and you just stack them up into one great big long feature vector, okay? You just have a great big long feature vector. They took a whole bunch of windows that somebody had drawn a little box around and said that's a pedestrian. Then they took a whole bunch of other little windows that said not a pedestrian. They played with rescaling things, etc., whatever, training it, and basically trained an SVM. And how well did it work? Well, obviously relatively well, or I wouldn't be talking to you about this. Here you see, taken from this movie, the ability to detect people. Here's some more of their work. You know, here's a snowstorm. I suppose it's in England, but I don't know. You know, you don't get too much snow. Here's another example, and every now and then you'll see a false alarm. Now remember, it's doing this all instantaneously. It doesn't remember anything from the previous image about there being a person in here. Here's another example. I'm not exactly sure why they chose these examples, but, you know, whatever. Now, you see where it's losing that person in the background? One of the problems there was that there was no gradient between the side of her dress and the dark background behind her. So it sort of failed in terms of the signal. And here you can see it, you know, pulling out some things and not others. A lot of work has been done to improve this kind of stuff going forward. Pedestrian detection has become a big deal in computer vision, partially because we have databases to train on and to test on, so you can compare your results to somebody else's. So that was pretty cool, right? You basically take this great big long feature based upon these HOG features, histograms of oriented gradients. You take a whole bunch of positive examples, a whole bunch of negative examples, you throw it into this training machine, you go get a latte, and then another latte, because it takes a little while, and it comes back and it says, here are your support vectors, here are the alphas. At testing time, just build yourself a feature vector, just take the dot product, multiply it by the alphas, I need some other sound effect, and sum them up. I don't know. Anyway, and then if it's greater than 0, call it a person. If it's less than 0, not. What if the data are not linearly separable? What if I can't just draw a line? Okay? So let's explore this, all right? So some data sets, linearly separable to start out with. So here I have them along a line. So I got my pink points on one side, my blue points along another, and yes, I could draw a boundary, and I would have I would have a margin between them. But what about something that looks like this? Okay, so here again, I've got 1D, right, and I've got my pink points here, but I have some pink points there, and clearly there's no single place that I could draw a line and say all the points to the right are pink and all the points to the left are going to be blue. So what do? I'm going to map to a higher dimensional space. Doesn't it sound cool when you say that? Map to a higher dimensional space. Well, here's a very simple example, all right? So here I just have the pink points along the single dimension x. What if I plot them in 2D? You might say, where does 2D come from?
Where does 2D come from?
She's on the ball now. Well, how about I just take x and x squared, okay? So I just take x and x squared. So these points are the same points, right? In other words, well, actually, this shifted over a little bit. This point should be right there. Yeah, these are pretty much, right? These points are the same points, but I just took whatever their x value was and just drew it on the x squared line. Okay? Well, that looks nice. Well, let's erase that. Now, is there a line here that separates the points? You know, a line that looks something like that? Well, if I push my magic button, there it is. Okay? And there's only 3 little support vectors, one here, and one there, and all of a sudden it's magically delicious. No, magically separable. Okay? So that's a pretty cool trick. It's about to get even cooler in a minute. Here's another example. Here we have a bunch of points. This comes from Andrew Moore. Pink points in the middle, blue points on the outside. And in the 2D space here, is there a line that separates them? No, of course not. But there would be this curve here, right, as drawn there. And that has something to do with sort of how far away it is from the center. Well, suppose I map, using some function cap phi, the points x to phi of x. And suppose that puts it into a space where along here is the distance to the origin. Now, and it's a little hard to see, the idea is that this plane in here is separating that. And the key to making this work was this mapping function, right? So we map phi of x, so it takes x from its original space into some higher space. That's actually called the lifting space, but it's to a higher dimensional space. Now comes the cool thing. And it's so cool we call it a trick. I mean, not too many things in science are called a trick. And this is called the kernel trick, all right? We saw that the linear classifier only depends on dot products. Remember that? I circled it, I jumped up and down a bit. So let's define some function k of 2 points, xi and xj, as just being the dot product, okay, between them, all right? If I map a data point to some high dimensional space, so my function phi here maps x to phi of x, all right? Then the dot product, whoops, I actually should write it this way, right? The dot product k of xi, xj would become phi of x transpose phi of xj. That's what's written right there, okay? And in fact, what I'm actually going to do is I'm just going to redefine k. Instead of just being the dot product of xi and xj, I'm going to have a new k, right, which is just this dot product of the higher dimensional space. K stands for kernel, okay? And it's a kernel function, and it can be thought of as a similarity function. Similarity functions, the idea is that they get bigger, more similar things are, and dot products can go from, you can either think of it as -1 to 1, which is true, so the idea is being the most similar is 1, least similar is -1, okay? And a kernel function is a similarity function that is the dot product, sometimes called the inner product, of the higher dimensional space. Okay, so I'm going to show you an example in a minute, but basically the idea is if I give you a function of x1, of xi and xj, some function k, as long as there's some higher dimensional space in which that function is just the dot product of that higher dimensional space, that kernel is a dot product, and therefore it can be used in our linear classifier. There's a whole bunch of theory there about what are called Mercer kernels, which have to do with what types of kernels are acceptable. You basically have to end up with these positive definite matrices between your points, a couple of other constraints. Most of that doesn't matter. What matters is that you have to is that you can show that essentially it's a dot product, and it turns out a lot of functions are. So let me show you an example. This example comes from Andrew Moore, and it's a really nice example. Suppose my vector x is just two-dimensional to start with, and I need to be able to say exactly how many dimensions so I can show you the whole thing written out. Okay? Let me define my kernel function as this. Okay, so my kernel function is just xi transpose xj, 1 plus that squared. Okay? This is referred to as a polynomial kernel because I take 1 plus the dot product of xi and xj and I raise it to a power squared. So this is the quadratic. Let's write out what that actually is. Okay? So we need to show that this function, in order for it to be a kernel that we can use for SVMs, it has to be a dot product in some high dimensional space. I don't actually care what that space is, but it must be a dot product in some space. So just for this demonstration, we'll actually show what that space is, but in general, we tend not to worry about that. All right? So here I just wrote out k, so it's 1 plus xi transpose xj squared. Multiply this whole thing out, okay? So just using the fact that x is only two-dimensional and it's x1, x2, you get this, big, ugly expression. And that's only squared. Imagine if it was raised to a higher power, or imagine if x, instead of being just x1, x2, was, x1 through x5, right? You get all of these terms, right? Here we only have 1, 2, 3, 4, 5, 6 terms, okay, because it's squared. But that expression can be written as the following, okay? And you have to sort of work this out for yourself, right? So let's just take a look at this term, okay? Well, 1 times 1 is what? 1, very good. So here I have xi squared, xj squared. Well, if I put xi squared and xj squared here, xi squared times xi1 squared times xj1 squared is xi1 squared, xj1 squared. This sounds like a Dr. Seuss thing, okay? What's going on here is, now let's take a look at this term here, right? These two times each other is that, and so on. Basically, this big expression is just this term, which is made out of the xi components, dotted with, transpose, the same term made out of the xj components. Okay? So the way of thinking about that is that's a dot product between the phi of xi and phi of xj, where phi of x is just defined by this. So here, the idea is we went from being a two-dimensional space to being a 1, 2, 3, 4, 5, 6-dimensional space. Now, we don't actually need to know that space. We're just going to use the kernel function in our SVM. And the way we're going to do that is we're going to use that kernel trick as, so instead of computing explicitly that high-dimensional space, right, we just define some kernel function, which we know is a dot product in a high-dimensional space, but we don't actually even look at it. We just know that it is. In which case, we convert our xi dot x for testing our new vector x to just the kernel of that. All right? And so we don't actually have to do the thing in the high-dimensional space. We just compute the kernel in the lower-dimensional space. So what are some examples of good kernels that become generals? Anyway, all right, fine. Well, the simplest kernel is actually just the original linear space, right? So if k of xi xj is just the dot product of xi xj, that's what I was showing you before for the Dalal and Triggs pedestrian detection, right? You just have a great big long feature vector, and I don't even have to map it into a higher dimensional space. I'm just going to assume that that's going to work. Now, and the number of dimensions is what? It's just n, where n was the length of the feature vector. So that's the lifting space. Now, something that I'm not going to teach here even in some higher dimensional space, for when you pick, your system might not be completely linearly separable.